All right. So we're taking a look at this example 1. So we want to show that the limit as our point approaches the center of x equals a, and then in b, the limit as our point approaches the center of y is b. So, we have some function. We have the center, which is our a comma b. So we're saying that the limit as our point approaches the center of x, the x should approach a. And then we want to show that for the second one, that as our point approaches the center, and we consider the y coordinate, that's going to approach our b. So we're just going to kind of follow this example. So then we're going to let p be the center, which is a comma b. So to verify a, we're going to let f of x equal x, and then let L be our a. So we need to show that for any positive epsilon, we can find a positive delta such that the distance between our point and the center, that distance, as long as it's between 0 and delta, then our function is going to approach the limit L. Okay. And then, so if we make those substitutions we just had, that's going to be the distance between x and a is going to be less than epsilon. So we need to show this. So if we let delta be epsilon, okay, so the distance between our point and the center, if the distance is less than epsilon, so then that means, so the distance formula, we have the square root of x minus a squared plus y minus b squared would be less than epsilon. So we could square both sides, and we'll get this line that you see here. Here. Okay. So then we square both sides, we'll get, x minus a squared plus y minus b squared is less than epsilon squared. So then, so we're just trying to isolate the x and the a. So now we have one positive thing plus another positive thing is less than epsilon squared. So then that means that at least the first one has to be less than epsilon, because you have two positive things that we add together to be less than another positive. Then you can take out one of those, the second one, and then that means that the first one is forced to be less than epsilon squared. So then when you take the square root of both sides, square root of something squared is absolute value. So now we have that the absolute value of x minus a has to be strictly less than epsilon. So in other words, so for any positive epsilon, we have that the distance between our point and the center is between 0 and epsilon. Then the distance between x and a is less than epsilon. Okay. So usually we have to find a delta such that when we apply it, it forces our function to be less than epsilon. That means it's really, really close. Let's see. So we'll have to revisit that notion a bit. I know that wasn't the best presentation, but let's kind of keep it moving, and we'll kind of come back as we need to. So the following theorem lists the basic laws for limits. We omit the proofs, which are similar to the proofs of the single variable limit laws. So theorem 1, assume that the limit as our point approaches the center of a function and the limit as our point approaches the center of another function exists. So we have the limits of two functions of two variables exist. Then the first one is the sum law. So the limit as our point approaches the center of the sum of two functions, so we can the limit of the sum of functions is going to be the sum of the limits. So the limit of the sum is the sum of the limits. So it's kind of like a distributing thing, but it's not quite that. But the idea is that the limit of the sum is the sum of the limits. The constant multiple law. So if we take the limit of a constant multiple times our function, it's almost like we can factor out that constant. So then it's like that's going to be the same as the constant times the limit of the function. Okay. The product law. If we take the limit of a product of functions, that's going to be the product of the limits. Okay. Now the quotient law. So if we have the limit of some function is not 0, then the limit of the quotient is going to be the quotient of the limits. Okay. Provided that g the limit as g the limit of g as our point approaches the center is not 0. So it's a single variable case. We say that f is continuous at this point if this function approaches the value function f of ab as our point approaches the center, as x comma y approaches a comma b. So let's look at continuity. So a function f of two variables is continuous at a point p equal to a comma b if the limit as xy approaches ab of our function is going to be equal to the value of the function at the point ab. So we say that f is continuous if it is continuous at each point ab in the domain, in its domain. Okay. So the limit laws tell us all the sum, multiples, and products of continuous functions are continuous when we apply them to f of x comma y equal to x and g of xy equal to y, which are continuous in example 1. We find that the power functions f of xy equal to x to the m, y to the n are continuous for all whole numbers m, and that all polynomials are continuous. So let's see, a rational function h of xy over g of xy, where h and g are polynomials, is continuous at all points a comma b where the function g is not 0. So again, it's like what we said before for rational functions. We just can't have that the denominator be 0. So we want to show that this function is continuous. Let's see, it's continuous as a figure 4. Let me see. Show that this function is continuous, then evaluate the limit as x comma y approaches 1 comma 2 of this function. Let me see. Okay. All right. So yeah, let's do this. So say we were here. We're going to take this and move to another page. We're going to keep this stuff above. I'm just going to work on another page. Okay. So we want to show that this function is continuous and then evaluate the limit. Okay. So so notice that, the top is a polynomial and the bottom is a polynomial. I think it is, yeah. Yeah, I don't know how to go as far as to say it's a polynomial. Yeah, the top is a polynomial, but the bottom. Well, here, let's look at each one. So if we were looking at 3x plus y, all right, if we're looking at that, are there any restrictions like that by itself? If we just had, z equals to 3x plus y, there wouldn't be any restrictions there. And then also, if we're looking at the bottom, there are no restrictions there either. So no restrictions on top and bottom individually. But then when we say the top divided by the bottom, again, we can't divide by 0. So we'll ask ourselves, okay, we would just have to find where the denominator would be 0. So let's see. For the denominator to be 0, so we would say something like, is x squared plus y squared plus 1, would it ever be 0? Okay. So now, you can kind of think about this intuitively. Any x that you plug in is going to be greater than or equal to 0. Any y that you plug in is going to be greater than or equal to 0, and then 1 is positive. So then, you got something that's always greater than or equal to 0, another thing that's always greater than or equal to 0, and another thing that's always positive. So, I don't think it would ever be 0. Because for it to be 0, it would have to equal 1 or negative 1, and we couldn't get the x and the y's to get to negative 1. Because if we choose negative values, they always go to positive, and if we choose zeros, the lowest that we can get is 1. So this shouldn't ever be 0. So then, so that means all x and y's would work. So there are no restrictions. So all our inputs. So we can basically, the domain would be all reals. We could take all the inputs. So it will be continuous everywhere, is what I would anticipate. Example 2. So the function is continuous at all points a, b because it's a rational function whose denominator is never 0. So therefore we can evaluate. So if it's going to work for all values, so then just to evaluate the limit, we can essentially just plug in the a and b. So then the limit as x comma y approaches 1 comma 2 of f of x comma y is essentially going to be 3 times 1 plus 2 over 1 squared plus 2 squared plus 1. Again, because no restrictions on our x and our y, so that's 3 plus 2 is 5 over 1 plus 4 is 5, 6, so it should be 5 by 6. It should approach 5 by 6. Let's see. Example 2.